Hello community! Let's talk about the new core of our AI agents. Now, today I prepared 3 beautiful new technical abstracts for you. We have here high dimension execution skill for dynamic agents in a continuous domain. Then we go here for an AI-driven review system by Stanford University, MIT, Columbia University, and Boston University. And finally here the most beautiful strategist learning strategic skill by LLMs via a B-level tree search. And we also have here the code available on a GitHub. This is by the California Institute of Technology, NEC Laboratories, University of California, Shenzhen University, and Rensselaer Polytechnic Institute. So here we go. We do 3 papers at once because we have AI that will help us to understand everything. Talking about helping us, I already have 3 videos about multi-agent devices for adaptive cyber defense. We introduced the regret gap, we found here methodologies, we looked at AI game theory, reinforcement learning. I showed you here that we can do synthetic science with AI, and I showed you 20 plus 2 new ways to code your multi-agent AI system. Now the last 2 videos were interesting, because if you have a look here, at the 25 minutes and 33 seconds in, I showed you how to self-improve, self-reflect, and self-learn agent new skills. And we were talking here about distributed AI computing. And here in the very latest, we showed here about how AI agents design themselves if we have multi-agent system. But now, you know what? You think, hey, this is all there is. No, we hardly scratch the surface of AI agent. This is so much more interesting than any LLM you can imagine. So let's start. Just for your introduction, we have here AI could make coders obsolete in 2 years, says the AWS chief. So great. So why should we do anything here about coding? And also I have to tell you that I just started days ago here with the new Cursor, cursor.com, the AI code editor, and I'm not really used to it. It's just at first testing after several days. I would say it's quite nice. Maybe you should have a look at it, and maybe you compare it to your Microsoft Copilot++, and maybe you might find this even more powerful. But of course, let's now focus on our 3 beautiful papers. Look at them. And normally I read between 100 and 300 titles and abstract of new AI publication every day. And you might say, why have you chosen these 3 particular papers? Now, it is easy. Normally, if you would like to analyze those 3 papers, we just vectorize here the complete information. We build a vector space, or we just add those papers to a vector space. We calculate similarity, we retrieve info segments, and we have the typical RAG system. And then I could analyze here the cross-cutting issues in those 3 papers. Plus, I have my videos. I input here my videos. I have supplement materials, maybe some other brand new AI studies. And then I would just go here with the RAG system and I would say, discover a new complexity core in all of those papers that are uploaded to my vector store. And RAG will come back to me and will fail completely. And you understand immediately why this level of complexity is beyond any RAG system today. Because remember, we go here with a similarity in an embedded space, in a, 1000 dimensional vector space. But there's nowhere about the core complexity of a paper. So you see, if you calculate the cosine similarity of this particular string of characters, you will find nothing. Now, we all know there are some approximation. You could say, hey, list the 100 technological items or functions or new ideas in each paper, and then you just compare about 300 or 500 different items, and you say, find the common denominator. And you try here, to approximate, to maybe understand, but you only have pieces. And pieces are not enough to understand the core complexity, especially if you do here a cross comparison when you do not know what you are looking for. And you want here that the LLM, the AI agent, is discovering this pattern. So RAG fails. Isn't this beautiful? We have an opportunity to learn. Now, we learn, and what I do when I learn, I go here and I Google here. Yes, I still Google, unbelievable. And I have here a new paper by Google DeepMind and University of Michigan from end of July 2024. And they do here the perfect thing that I'm looking for. They have the retrieval augmented generation or the long context LLMs, like Gemini with 2 million token context length. And they compare it. And as you can see already here, without reading anything, you see here for GPT-4 Omni, this in RAG here, in this little pink, this is the performance, 32%. But if I go here with a long context, I'm close to 50%. Gemini Pro, the same. RAG gives me 37%, but long context, 2 million token, gives me 50%. Now, maybe there's a cost advantage if you do RAG, but for today, I spend $2 to $5 to have this new topic explore and understand why I've chosen these 3 particular papers. So authors Google DeepMind tell us here, long content consistently outperform RAG in terms of the average performance. So we go now with this. So what it means, we move now from a code complexity for our AI agents. And you've seen AWS here, CTO told us, hey, don't learn to code because we will have here automated AI agent to write the code. And we just talk in normal plain English and the code is written for us and that's it. So we move from the code complexity to the design complexity of AI agents or multi-AI agent with logic functions. So do not underestimate the step that we're going to take today. Now, beautifully, if I want here to understand what is here the new idea, you're not going to believe it, but we do have a paper here by Stanford, MIT, Columbia, and Boston University where it is exactly on topic, because it is here about LLMs that do academic reviews of academic scientific papers. And I say, hey, I just use this code here to understand what is happening and why RAG fails. And here we have the prototype of our PDF too. We upload here a PDF and we get here a review, an official structured review by an optimized AI agent. And you see here we have soundness, presentation, contribution. But the other system gives us a different soundness and contribution. And the structure here, look at open review. You see exactly summary, soundness, presentation, contribution, strength, weaknesses. And the process is, those are the human reviewers on top. And then you have 3i system. And this is the way that this system learns. Now you have here the strength of this publication, of your research. Here you have the weaknesses of your research by a specific AI agent trained to evaluate scientific publications. You have open questions that you can learn from. You have here your ethics review. So if there's any problem, the LLM will tell you. And you have a rating of 8 out of 10, so you pass and you have a high confidence level. But look at Model B on the right side. The rating is 4 out of 10. So this LLM tells you, you fail. Your research is not good enough to be published. Look here at the questions. You see the questions are not identical to the other one. The system focuses here on different topics. If you look at the weaknesses of Model A and Model B, you see the weaknesses, the AI agent focusing on different points. So if you could answer the weaknesses on A and the weaknesses on B, that would be great. So you can improve here your performance given what other reviewers did here on similar topics in your domain expertise. And the LLM learned here the other human evaluators to simulate the human evaluators. So I say here, I think A is better So I submit here my vote here for an agent, and you see it was GPT-4 Turbo compared to Claude 3 Opus. So beautiful. So let's come back to our 3 papers, and you have it here. 1, 2, 3, and we had a look at paper B or PDF 2, our AI-driven review system, where our agent told us here it simulated a human reviewer or multi-human review process complexities here by our new AI agents. Now, what you immediately understood is that the performance level of that particular agent is the dominant factor for the output quality of the review. If you have a better agent with a better LLM, then your output quality increases. Do this test for yourself. Go with a simple Llama 3.1 and then go with a Gemini. You will see significant differences in the output. So what does it mean? This means that our agent, and remember, we are talking here about agent and not about LLMs, that our agent skills, sometimes we have to find where the agent skill, let's say on a scale from 1 to 10, is it on 3 or 4? And maybe there's a threshold for the methodology to work. So we have to upskill our AI agent. So this means we have to find out, we have to have an estimation of the agent skill level. So, and if we say, okay, it is just at 3 and we have a threshold, I don't know, at 7, so we have to have some self-refinement of the agent, some self-reflection of the agent, and some self-learning of our AI agent. So then the performance of this little agent that does here the review system is increased, that it goes beyond the threshold to be operational. And it depends on you where you put this threshold for your system, for the quality that you want to achieve with an AI review system, where the machine evaluates the human scientific progress and the human scientific update reports on a particular domain. So you see, this is happening, as I told you here, the review system, beautiful. And then what a coincidence. Do you know that the title of the first PDF is Agent Skill Estimation of High Dimensions? So this is already here the right place. So our first PDF exactly will tell us how to do the agent skill evaluation and the estimation of the agent skills. And we're not talking about the LLM performance. We are talking now about the complete complex agent. And then, what a coincidence, we have the third PDF paper here, The Strategist by California Institute of Technology. And you know, here it is about to develop strategic skills in AI agent for multi-agent configurations, like a multi-agent game environment. And we will use here different intelligent systems. And we'll use here different mathematical approaches to develop here new improved strategic skills for particular agents in our multi-agent environment. And yes, you guessed it, maybe we use here a little bit of game theory for the development of our strategic skills, the upskilling here of our agents in a multi-agent configuration. So this here gives you now a beautiful overview why I have chosen those 3 papers. I just wanted to go here to show you what an agent can do, that there is a methodology to assess the quality of one single agent, then to self-learn, self-reflect, upskill this agent to a certain threshold. If we go here for a dynamic, for a continuous action space, and we will do this here in a time series also, so we are not in a static space. And then we apply what we learned here for a single agent. We will integrate this with game theory and a multitude of other theories here for new strategic upskilling in multi-agent configuration. And you might say, hey, that sounds simple. Yes, absolutely. So again, core objective 1, 2, 3 is clear. Now, what is the primary methodology? We will go here with PDF1 here, with a Monte Carlo skill estimation, using here particle filtering in a dynamic network, in a particular network, in a causal reasoning network. And for the strategies, we will also look here at a Monte Carlo, but now a tree search methodology that is combined with an LLM-based reflection and a self-improvement methodology. Never mind, just want to show you there is something in common that we're gonna have a detailed look at later. And probabilistic models used, yeah, this will be our models. This will be our Monte Carlo techniques, this will be the inference mechanism, and we will have a dynamic adaptation we're going to talk about. I'm going to show you here the strength, the complexity, and the challenges we will inquire, the shared teams, which RAG failed to establish, and the differences here in the focus on the paper. But we can learn now with the help of AI. We just study one paper. We will study 3 papers, and maybe in my next videos we will study 4, 5, 6, 10 papers in parallel with the help of AI. But we know how the AI system works, how our agents, what skill level they have, and maybe I will have to upskill here the performance level of 1 or 2 agents to achieve better results. So you see, if we would put all of this here in a RAG system, we will build our beautiful RAG vectors, but you know what? Now we don't need them anymore, because we have this beautiful study by Google that tells us, hey, long context is in the performance better than the RAG system. And as I told you, for the moment we ignore the cost to ratio performance. Great. So let's start here this idea. And you know what? I just want to continue here from some of my last videos where we talked what is an agent, what constitutes an agent compared to just an LLM. And surprisingly, we will discover a whole complexity inside an AI agent, and this is why we're here. So let's just recap what we learned in the latest videos. What is an AI agent? It has, if you want in a mathematical notation here, a simple function of some parameter. We have the perception, then we have tool use and function calling. We have a particular knowledge representation and reasoning capability. We have the learning capability, the planning capability. We have the action execution going on. We have, especially if we go in multi-systems, a goal management, and for multi-agent, communication is really important. So if you want to reduce it to the max, what are the essential building blocks for an agent? Those are here the functional capabilities of our agent. Talking now about the structural capabilities, you know that every agent at its core has a little AI model. Could be GPT-4 Omni, could be any, I don't know, Gemini that you like, or any Claude system that you like, whatever you go. We just call it an AI model. Now you understand, and I made it a little bit clearer here, what it does. For the perception is powered by an AI model. For tool use and function calling, this is guided by our AI model. For the knowledge representation, for the specific vectorization and the reasoning, the logical reasoning, this is enhanced now by the structure, by our AI model. Now, learning is of course driven by it. Planning is here informed by the AI model, whatever the AI model was trained on. The action execution is selected by our LLM. The goal management is, of course, prioritized by the internal parameterized knowledge of our vision language model, and the communication that is so essential if you have a higher complexity with multiple active agents. This communication is, of course, generated by our AI model, an LLM or a vision language model, or vision language action model. So you see, now the complexity suddenly increases. And you know what? We found out that if we want to tune now the performance of an AI agent, we have to know what element, what function we have to start with, because you're not going to believe it, but the learning depends on the knowledge representation, on the tool use, on the perception, and on the planning plus. So this is not a single function, but this is a function of function where we have an interconnectedness and an interdependency in the learning process. So, yes, if you studied mathematics, you say, hey, I know solution to those systems. Yes, of course. And we are not just gonna look at it if we have a single AI agent, because I already did all the videos on multi-agent compound system. So why limit ourselves just to a single agent when we can do multi-AI agent optimization and we choose particular agent to optimize for our particular task that we want? Now, for my little green grasshoppers, never mind. I have given here you a little bit of additional information. We have the same perception, tool use, knowledge, reasoning, learning, planning, action, execution, global management, and communication. But I explain what the AI models, your large language model, your vision language model, or your vision language action model, does as the central intelligence of this system. So we are now focused, hey, we want now to improve the functional capabilities of our AI agents. So gone are the times by simply doing some LLM optimization. Now we want to improve specific function of a complex system that constitutes an AI agent. Or in short, we upskill some multiple AI agent depending on their interconnectedness. Now, from literature that we know for years now how to estimate here the agent skill level in a continuous action domain. And we have here some frameworks, BICE. And those skills are then, for example, here in two different categories. Classical way was the execution skill. This means how well the agent can perform an action in its environment, and a decision-making skill. How well the agent chooses which action to perform next given the planning capacity of the agent. And the focusing was on developing and evaluating those methods to estimate those skill levels. Because, let's say, if our execution skill level was 2 out of 10 and the decision-making skill level was 8 out of 10, if I want to optimize the system, you know exactly what to focus on to optimize the complete complexity. Yes, I know you are thinking back and you say, my goodness, good old days, how simple was it just to evaluate a single LLM just on a simple benchmark and have a performance indicator. And now we have to do this on interdependent function and sub-function and interconnected and intercommunicating parameters for at least one AI agent, and then maybe we do it here in a multi-agent compound. So you see, AI is starting to get really interesting, and we leave those little LLMs behind. Now we want to create value with our AI knowledge. You know that this AI agent, the simplest explanation that we were looking for in my other videos here, now we are only focusing here on the execution skill, so the action execution and the decision making. Now, I make it a little bit harder for us because now that you are an expert in AI, you know that is directly connected here to the planning capability of the planning functionality, where the agent decides what step to take next, what to decide, which actions and step to take next and execute this. So we are looking here just at two of our functional capabilities. And they turned out to be real complex and interconnected. So let's start with two before we expand here our methodology to optimize multiple subsystems with a sub-functionality and then have a beautiful complexity that performs our task. Now, from the literature, if not, never mind, my little grasshoppers, I have here for you. We call it a joint estimation of execution and decision-making skills, JEEDS. This is a method that estimates both the agent's execution skill and the decision-making skills simultaneously. We use here the reward information to utilize here to reason about the agent decision-making skills, and the executed actions give now here, what they provide now the insight into the execution skills. So we just watch what the system is doing, and then we can understand what maybe was going on. So yes, we are here in a probabilistic system. And this JEEDS method was shown to produce far more accurate skill estimates for the agent across here the complete spectrum of rationality levels. If you want to read more about the latest one, this is our PDF 1. This is here the link for you. Now, before you read here our PDF 1 of this video, please note that the authors here, they are researching this topic now for 5+ years. So I have here the Journal of Artificial Intelligence Research from May of 2024, and I know that all of you read here the Journal of Artificial Intelligence Research. But look, this was submitted in August 2023, and they here showed us in 60 pages how to estimate here the agent skill in a continuous action domain. And if you want to study more about this, those 60 pages are essential to really understand today's paper. Now, show you here 6.2, they explain in detail the joint skill estimation, the JEEDS methodology, and they show you here they will compute the joint distribution after every newly observed executed action, and the derivation will specify this computation for a particular sigma and a lambda skill combination in terms of the components that have previously been defined. We have here Bayes' rule simply, and then we go on with mathematics, and those are 60 pages that give you a real deep dive if you really want to get here to the core of this functionality. For my green grasshoppers, never mind, give you here the short introduction. Why do we need JEEDS? Now, you know that we have a conditional dependency in our system. So this means the ability of an agent to make a decision and execute those, they are often interlinked. So a high decision-making skill can lead to better targeted actions, while high execution skill ensures that those actions are performed effectively. Now, if we estimate those just two skills separately, we overlook their interaction, their dependencies, which leads us to an overall not accurate skill assessment. So we have to find a solution. And unlike simpler methods that came before JEEDS, that assumed here perfect rationality or required expensive domain-specific tuning, JEEDS helps us here is more robust and more generalizable. Now, how does it work? We do have here a Bayes network. We model here the relationship between the observed actions and the underlying skills. And we just go here for two, the execution skill and the decision-making skill. So the network includes a node for decision-making skills, which influence the choice of target actions, and a node for execution skills, which affects how closely the performed action matches here the target actions. Now, of course, we have to have a joint probability distribution working with this between the execution skill sigma and the decision-making skill lambda after observing now n particular actions of the system. And this distribution is updated using now here Bayes' rule whenever a new action is observed. Now, if you're not familiar with Bayes' network for my real young green grasshoppers, if you start brand new, I try to explain it to the best of my knowledge. Now, those networks, they're ideal for taking an event that occurred and predict now, probabilistic, the likelihood that any of several possibly known causes was here the contributing factor that this event occurred. Let me give you an example. A simple Bayes network could represent a probabilistic relationship between diseases and symptoms. You know this. Now, given the symptoms, the network can then be used to compute the probability of the presence of various diseases. And the highest probability, hopefully, if we have coded it correctly, will give us here the disease that aligns best with the symptoms we detect in the real-world environment. Now, you understand, talking here about causes as contributing factors that something happened, we are here talking here in the easiest mathematical representation space of causal networks. And causal networks in general are special cases here of the Bayes network. Great. What else do we have here if JEEDS is working? We have an update process for our beliefs. So the update process involves calculating the probability of different skill combination based on the observed action, the previous belief that we have, and the reward associated with each possible action. This ensures that both execution and decision-making skill are considered together, leading to a more correct estimation. And of course, like you notice, we have now working with joint probabilities for all possible skill combination. We have to normalize the results because this is easier, faster, and it gives us a better insight to understand and interpret here valid probability distribution of our complete system. This was it. Beautiful. So what we are now going to do, the next step for us here is we take JEEDS and we will, as is shown here in PDF number 1, we will include now a dynamic system. We will have here a time series evolution of our network. So with a new time dependency on some of the parameters or selected parameters or maybe all parameters, this thing gets really interesting. But there's a problem. If we now increase the complexity that we have to compute, there's a certain threshold where we can't solve it anymore analytically, or we can't solve it in a normal compute time. If we take, I don't know, half a year for one step, the complexity simply becomes numerically too difficult to handle to solve it in the correct analytical way. Therefore, we are now faced with a problem, and this problem, even if you say now, hey, but I have access to 10,000 NVIDIA GPUs, I have pure compute power. Well, you can't solve it analytical because the complexity is so high. Even if you put 1 million NVIDIA GPUs on the topic, we have to find a new intelligent way how to do here our agent optimization. And you know what? Even if we now go a next step and we include now the multi-agent interconnectedness in this topic, I will show you here a new solution in my next video, and I think I will release it tomorrow. So there you have it for today, a short introduction to the topic. If you want, go and read here about JEEDS. It is a little bit a dense mathematical compendium here, but it really gives you good insight what are the methods we use today for AI agents. And remember, we left our LLMs a long time ago. We moved over to agents, to real complex agents. And now we have to handle the complexity that is inherent to those agents. But you know, the step from a single LLM to an agent system, the beauty is we have so many additional functionalities we can add. We can improve now the performance of the complete system that we have to find a way to handle now even the higher complexity of our AI agents, especially if they interact like in a real-world environment with multiple agents and different agents, and maybe we have a human AI interaction. So we have to train our agents better. We have to make them more clever, if you want, in a particular way. We have to balance their individual performance whenever they act in a group, in a swarm intelligence, and we have to find an optimization. And then, if we have this, we have to find a new methodology that we can't compute today, but there is a way that will solve all of this. And if you want, we will have a look at this in the next video. It would be great to see you.